All right, so just to recap real quick, the last notes you copied were very short, very colorful. Make sure you color your pH scale. We're going to be coming back to it later and talk about what those numbers mean and all that stuff. But basically, I just wanted you guys to see the difference between acids and bases, just like the physical properties that you're actually able to see or taste, right? So it was just for that, to kind of give you a basic foundational knowledge of the difference between acid and bases, which you probably already are familiar with because you have heard or learned about it before. But now let's do a deep dive into acids and bases. So we're going to start off with acids. We're going to be talking about acid dissociation. I feel like it sounds a lot harder than it is, but dissociating means it's dissolving, it's coming apart. So we're going to be talking about acids that are coming apart in a reaction. Okay? So there's I shouldn't say two types of acids, but we focus on two acids that were categorized specifically by two different scientists. So first we have Arrhenius, who said he defined acids and bases specifically. So with acids, he said that acids produce H plus or hydrogen ions in aqueous solution. Remember, aqueous, which I guess I'll write out this first time in case you need to see it. Aqueous solution. Remember, aqueous just means it's liquid form, okay? It can have a little bit of precipitate, if you could recall to that lab we did, but it's still more liquid than solid, right? So we have aqueous, which is liquid-like form, and then we have solid, liquid, and gas. And he stated that bases produced OH ions, or hydroxide ions. Okay? But then, these two other guys came. One of them, last name Bronsted, which it actually has that line there. Like this. Hold on, I need to make the O bigger. Bronsted. It actually has that line there in his name, printed in the book. Lowry, acids and bases. So here they stated that the acids, they are the proton donors. Proton referring to hydrogen, H plus. Okay, proton donors. Bases are, can you guess? Yes, the proton acceptor. H plus acceptor. Okay. So we have these two types. I believe it's easier to use the Bronsted-Lowry definition. I feel like it's a lot simpler, and typically teachers will focus on this type of acid and base, how these are defined. But if we're looking into a reaction and how it's dissolved, let's do one real quick of HCl dissolving in water. So for example, if we have HCl dissolving in water. So just so you can get a visual of this, so HCl dissolving in water, which is H2O. I'm going to draw it out so that you can physically see what it looks like when they're donating or accepting a hydrogen proton, okay? Or a proton, a hydrogen ion, sorry. So say we have oxygen, right? We have water. We're going to go back to Lewis dot structures briefly. HCl. Chlorine has 7 valence electrons. Then we have 3 has 3. Then we have water, we have HCl, then we have H3O+, and then we have Cl-. Ends up keeping an extra electron, which makes it minus, okay? It's just a visual for you to see that our H2O here, right, became H3O+. Why? What did we lose? We lost this hydrogen. Okay, this hydrogen added to the water, and that's why we have chlorine by itself and we have the extra hydrogen here. Okay, so which one's the proton acceptor and which one's the proton donor? Proton acceptor is the H2O. Proton donor is, this is your proton acceptor and this is your proton donor. So which one's the acid? This one. And this one's the base. Okay, so again, the proton donor, because it lost it, right? The hydrogen is always going to try to attach to the water molecule. Why? Because it's polar and all the charges that water has. It's going to try to take that H here. And because it's accepting it, that makes it a base. Okay? Alright, so the overall reaction when acid dissolves in water, let's take a look at that real quick. So we have overall reaction when acid dissolves in water. Okay, so this is a generic or general reaction. So we're going to have HA aqueous plus H2O. Alright, so the overall reaction, HA aqueous plus H2O liquid. And then we have H3O plus aqueous plus A minus. So typically, I was going to do this, hold on, I was going to do another color. So typically when you have a dissociation of acid and water, this is what the reaction is going to look like. So let's talk about the different parts of the reaction real quick. We have 1, 2, 3, 4. We have 4 total substances. This here, if you recall too when we were naming acids and stuff like that, any substance or compound that had an H in the front was automatically an acid. So this one is the acid. So if that's the acid, that means this one has to be the base. And then this substance or chemical that is accepting the hydrogen from the HA over here, that's going to be our conjugate acid. And this one here, the A minus, the one that lost the hydrogen, the proton, is going to be your conjugate base. And just real quick, these arrows, when they're half arrows and they're going both ways, it means that it's reversible. So it can go both ways. It can go from left to right, right to left, and it's at equilibrium. It's balanced. Okay, so those two things. The conjugate acid, so just to define these, the conjugate acid it's formed when proton is transferred to the base, and conjugate base is, you can probably assume, is what remains of acid molecule when the proton is lost. When proton is lost. So you're going to have these four. When you have acid dissociation of water in water, you're going to have these four parts to it. So if we were to, and then lastly we have a conjugate acid-base pair. What does that mean? It's an acid-base pair. So in these two, our H and our A, and our H2O and H3O plus, these are our conjugate acid-base pair. And so typically what you will see, and I'm going to write this down, you don't really have to worry about it yet. We're going to go into it more in depth later, but you are going to see it. So you're going to see this Ka equals H3O plus A minus over HA, but then we simplify it to be H plus A minus. Okay, and this is describing the reaction at equilibrium. So reaction at equilibrium. And this here, the Ka, is it's our acid dissociation constant. And again, we're going to see this more later on. So I wouldn't worry too much about it later, but I want you to start seeing it. And real quick, these brackets here, these square brackets, are referring to concentration. Okay? Concentration, these square brackets. So this is just showing that the concentrations of these acids and bases are at equilibrium. And here we have H plus. We can get rid of the H3O plus because in water we can assume that our concentration of water stays the same.